Why do we so often speak about impulse response and step response in system theory, control engineering, and technical dynamics? And why should we be interested in how a system reacts to such simple and seemingly trivial signals? Let's answer these questions using an intuitive example without introducing unnecessary mathematics. We consider a dynamic, linear, time-invariant system described by its transfer function g of s. As an example, take a car that can only perform vertical motion, for instance when driving over a bumpy road. This system can be simplified as a vertical, single degree of freedom oscillator. The base displacement is described by u of t, and the degree of freedom of the vehicle body is z of t. The transfer function g of s in general describes the relationship between the output quantity, here z of t, and the input quantity, here u of t, in the frequency domain. Now consider what happens when we apply an impulse to this dynamic system. For example, when the car passes over a short bump. Does the system oscillate strongly or only slightly? Does it return to a stable equilibrium state? And if so, after what time? These are exactly the types of questions that the impulse response answers. For this purpose, the system is excited with a short impulse, and the resulting time response reveals important information about the system behavior, in particular about its stability. We can perform the same type of analysis using the second extremely relevant test signal, namely the step excitation. In this case, imagine that the vehicle drives onto an elevated platform and remains at this higher level. This corresponds to a step in the input signal. Does the system start to oscillate and possibly become unstable, or does it return to a stable state after a certain time? How much does the vertical motion overshoot beyond the excitation level? All of these questions can be answered using the impulse and step responses. The system response is shaped by the system parameters like mass, damping, and stiffness parameter and their ratios. Before we move on to the visualization of different impulse and step responses, if you want to truly understand how to step-by-step analyze and interpret dynamic systems with confidence, check out the first link in the description, where you will find a bunch of interesting real-world engineering exercises. The system response in a time domain is simply the inverse Laplace transformation of the product of transfer function and input signal. If we plot this response over time for a step excitation, we observe the following behavior. For a damping ratio of d is equal to 0.1, the system oscillates for several seconds and overshoots significantly beyond the step height. If we increase the damping ratio to d is equal to 0.3, the overshoots becomes much smaller and the system returns to equilibrium much earlier. For a damping ratio of d is equal to 0.7, oscillation is almost suppressed. The overshoot is small, and the system returns to the equilibrium state within a very short time. The same qualitative behavior applies to impulse excitation. This concept can be applied to any type of dynamic system. Very often, controlled systems are analyzed with respect to stability by investigating how a mechanical system reacts to an impulse of force, or how an electrical circuit reacts to a sudden connection to an external energy source. Impulse and step responses, therefore, provide fundamental insight into stability, damping behavior, and transient dynamics of linear systems.